All right. Good morning, everybody, or good afternoon, or good evening, wherever you are in the world. So let me see if I can share my screen here. Can you see this okay?
Yes, we can see it.
Yes.
Okay. Well, first of all, thank you for the invitation, Rafiq, to give this lecture. I am a department chair and professor here at Auburn University. I'm in Alabama in the U.S. So this is early morning, and so what we're going to cover today is really the second stage of the three-stage approach that Rafiq has introduced, and we're going to focus on design of equipment using the reverse design approach, like Professor Ghani just mentioned at the wrap-up of his talk. There you go. So the three-stage design methodology really is comprised of the process synthesis stage, the design stage, and the innovation stage, and that's what's being covered in the workshops and webinars over these 3 days, yesterday, today, and tomorrow. The synthesis stage is really focused on finding the optimal processing route to convert raw materials to products, which is what Professor Grossman's lecture focused on yesterday. The design stage is really the portion where we do detailed simulation and analysis to identify potential targets for improvement, which is what we'll talk about today. And then the innovation stage is what Professor Pistakopoulos will focus on tomorrow, where we're looking at new alternatives that match these targets for improvement. And so that's the overview. So if we start by just setting some definitions. So in chemical engineering and design, we base everything on unit operations. Process synthesis, the way Professor Westerberg defined it, is really to find the optimal process from all the different alternatives that can convert a set of raw materials to a set of desired products, subject to whatever our process specifications and performance criteria is. And what that means is it's really the exercise of combining and sequencing and ordering the different unit operations to satisfy our objectives. There's a lot of different ways that this can be done. So this is just a superstructure here of all the different pathways that could be taken for a set of raw materials to be processed into a set of products. And the synthesis portion is really to identify which of these many pathways is the right one to choose. Looking at design is really to then, for that option, to find the optimal values of the various specifications and design variables that will allow us to get us there. And that will eventually lead us to a optimal flow sheet. So once we have a flow sheet, that's where we're doing the detailed design calculations. So the synthesis process step will give us a potential flow sheet. And then the next step is to determine the design variables so that we can do process simulations, so we can do the detailed analysis, whether it's economic, sustainability, life cycle analysis, and so on, which is what Professor Ghani will cover in the next lectures. Once we have this base case simulation, we can identify any hotspots in the process where we may be using more energy than necessary, or where there's opportunities for improvement. So this is really the steps that the second stage goes through and what we're trying to accomplish. So again, the objective is to calculate all the design parameters so that we can fully define the flow sheet, so that we can do rigorous simulation, not just shortcut simulation or simple mass and energy balances. We want to do full rigorous simulation. When we look at the reverse simulation approach, which is what we'll focus on today, we use a series of methods that allows us to obtain these design parameters to describe the flow sheet, but do this in a more effective way and a more logical way. Everything from reactions, separations, heat exchangers, pressure changers, and so on. So starting point, you have some kind of structure representing your process. This is a simple mass balance model here. This is for the hydrogenation of benzene to cyclohexane. And right now, all that's there is a general structure of the process where feed streams and recycle streams are mixed, sent to a reactor. The output is sent to some kind of separator, and we have a product coming out, and we have a gaseous stream coming out the top. Some of it is purged, some is recycled. That's really all we know at this point. The next step is then to look at, okay, how do we convert this into a model that's more suitable for mass and energy balances? That means we have to include any kind of pressure changes, temperature change units, and so on. So now we start getting a little bit more definition into the structure. The next step is to take this representation and convert it into a more defined flow sheet where we actually add the stream definition and any operation data for the different units. That would be, outlet pressures, temperatures, reactor conditions, pressure drops for separators, and so on and so forth. The key thing here to remember is that how we do this second step is highly dependent on the choice of process simulator. Each process simulator, while they solve the same problems, they go about it in somewhat different ways. The model specifications are going to be a little bit different in terms of how they're set up and what kind of information is necessary. And we'll talk about that here in just a minute. So this is just a recap of the 12-step sustainable process design process that Professor Ghani has introduced. There's a whole series of decisions that we have to make when we do design, starting from what was covered in Professor Grossman's lecture and in the workshops yesterday, which is really the first step is the process synthesis, where we have to define the raw materials, the reaction pathways, and the specifications on the products. And you'll see some tools for this, ProCFD and SuperO for superstructure optimization. And out of this comes this initial flow sheet or set of candidate flow sheets. The next step is then to go to the simple mass balance, where we need to put more specifications on the reactions, separations, and so on. That will give us the flow rates of all the streams for all the components in there. The next step is then to add the energy balance, where we add stream temperature, pressures, and states. Now we can define the various stream temperatures and pressures. We can specify the units needed in terms of compressors and pumps and so on. And that really lets us define the necessary information in order to move into rigorous process simulation, where we typically look at commercial tools like Pro2 and Aspen. Here we need to have identified all the design parameters for every piece of equipment and unit operations in there. Once we've completed this task, we will have a complete stream summary for the flow sheet. That means all states, all input Ps, and so on, which we can then use for the analysis step. That's where we get into looking at economic analysis, setting design targets, whether it's in terms of economic performance, sustainability performance, and so on. And then the last set is where we look at coming up with new, more sustainable options, looking at different performance criteria and finding out if there are further improvements we can make, and finally make a decision on what is the best solution for the specific problem that we're trying to solve. So in this lecture, we'll focus on these steps from 4 to 7 in the middle. Steps 1 through 3 were covered yesterday, and Professor Ghani will cover tasks 8 and 9 in the next webinars, and Professor Christopoulos will cover 10 through 12 tomorrow. So like we talked about, what we need to specify depends on the simulator software and the specific model that we're trying to define. But some general things that we will have to do, we will have to specify the chemical system. If it's a mixture, we will have to make sure that we have all this described correctly. All the unit operations we will need to describe in whatever format is necessary to give the right level of detail. The flow sheet will have to define, that means all the interconnections, all recycles, and so on. And we do this through a series of models for the unit operations, the thermodynamic property prediction, the type of method of solution we're going to use. Are we going to do sequential modular, equation-oriented simulation, and so on? Those are general steps that are not specific to a certain piece of software. They all do this in some shape or form. They may do it slightly different, and the user interface might be slightly different, but the same steps will have to take place. As a designer, you need to make design decisions. That means, what parameters are we going to specify? What values do we specify for them? And we will do this by selecting different options in the simulator. And we'll talk about some combinations of choices in this talk. So here's just a couple of slides. We're going to cover some available options in the various types of process simulators. So here's a list of thermophysical properties that can be described, and the model or algorithm that is used to calculate those. That goes back to the question at the end of Professor Ghani's talk. How do we handle the thermodynamics for these types of systems? And all process simulators have a vast array of physical property models, ranging from equations of states to activity coefficient models, to a variety of other Gibbs free energy minimization approaches, and so on. And they can calculate a variety of properties. There's only a very, very partial list here. But the choice of model is extremely important, as Professor Ghani said, because it really specifies and determines the application range of what we're trying to solve and the validity of the solution that we get. This is not something that we're going to cover today. We will talk briefly about the roles of these models as part of this talk, but really we're focusing on unit operations today. There is another webinar series in a couple weeks, webinar 2 on July 27th, that focuses on properties estimation, where this will be looked at in much more detail. The only thing that we wanted to really show here is that there is a large list of models available to choose from, and the choice of model is extremely important. So when we get into the unit operation representation, all these different types of process simulators have a range of modules, ranging from very simple modules like we're seeing here, simple stream splitters, and they're shown here for 3 popular commercial simulators, Aspen Plus, Pro 2, and Unisim. These simple unit operations are really exactly that. They are simple. They don't include full calculation of enthalpies and state variables. So, you know, a splitter, the divider here, you can basically split a stream with no combination. At the bottom, you have the separator, where you can specify separation fractions at any arbitrary rate without having any physical relationship with them. You can literally split any stream into any set of constituents. But again, this is for simple mass balances only, and not to do energy calculations or even enthalpy estimations. Similarly, for reactors, you can have the simple stoichiometric reactor, where all that's needed is the feed stream specification, the reaction, and the level of conversion, and that will give you the output. And if we move on to more rigorous models, then you can take something like a heat exchanger. The simple ones, it's just a heater or cooler. All you do is specify the outlet conditions for a given feed stream, and it will calculate the enthalpy change needed. You can also do more complex representations like shell and tube heat exchangers, where you have to specify both the utility streams, the process fluids, and so on. And you can increase the level of complexity depending on the need. When you're doing process synthesis or initial analysis, then typically the more simple models like the heaters and simple heat exchangers that are shown at the top row here are sufficient. But once you get into doing detailed design, once you've selected a candidate flow sheet, that you want to explore further, then you need the more complicated and more rigorous models in order to get better sizing estimates and economic performance. So here's just a couple of comments. So for reactors, for the simple models, you just need the stoichiometry and the conversion of the key compound. When you move into the rigorous models, it basically represents the same information, but then you add the temperature and pressure dependence. You can also add kinetics, which at the end of the day will calculate some representation of the overall conversion and give you a better estimate of what is the outlet and effluent of the reactor. When you get into temperature or PT flashes, you're looking at the separation factors for each compound if it's a simple model. But when you want to include more rigorous calculations, you need either temperature and pressure or the pressure drop. What's important here to notice is that you can only specify two parameters of the temperature, pressure, the split between the vapor fraction, the energy duty. But this is one of the strengths of a process simulator. If you're solving this in a classic forward manner, what you would do is you would iteratively set the conditions, temperature and pressure for the flash, and evaluate the outlet streams. But because the simulator solves the same set of equations regardless of which parameters you specify, it's much more effective to specify the desired split that you're looking for and have the simulator calculate the missing variable, which could be the energy requirement or the temperature needed or the pressure needed. So pick two, but rather than having to iterate, you pick one that's specified and you specify the one that you want from a performance perspective and let the simulator calculate the remaining variables. Moving into distillation, for simple models, all you need is the separation factors for each compound. But when you do rigorous models, you need much better description of the column, the number of stages, the location of the feed, the conditions of the feed. You need the pressure profile, you need the draw rates, you need the duties of the condensers and reboilers, and so on. And those are just the minimum requirements to represent a column. If you get very complicated systems, you need to also specify the internals of the column, the types of baffles, the types of column internals, the stages, and so on. Everything from the weir height to the downcomer size, all those things are going to be necessary when you get into trying to calculate hydraulics, calculate the size of the unit for economic purposes, and so on. Heat exchangers, you don't need those in the simple mass balance model, but when you go to the rigorous model, you will need the exit temperatures and pressure drop. You can also do this in many other different ways. Compressors, you need the outlet pressure and efficiency of the unit. Same for pumps. If you just have a simple divider, that's easy because all you need is the amount relative to the feed that is going to each of the outlet streams. These are typically also used for purge streams. And the key thing to remember here is that these are just literally stream splitters. You don't have any changes in composition, only flow rate. So I wanted to say a few things about property models because it does impact what we're talking about in the reverse design approach. So what does a property model do? If you take it by itself, you have information on temperature, pressure, composition, and component IDs, and the property model will calculate the properties. That is what is then linked to the process model, which describes the raw material conversion to products in its very simplest form. If you solve this model more than once, you're basically doing simulation. So you specify some design parameters, you get some results out, and if you're happy with the results, you're done. If not, you update the design parameters until you get the results you're looking for. If you use structured and systematic methods for doing and specifying the design parameters, then really you're doing synthesis design similar to what Professor Grossman talked about and what we'll cover today. In this scenario, the property model provides a service to the process model. So every time a property value is needed to solve the problem of converting raw materials to products, there is a call to the property model and it calculates those properties. But once we have a method for doing structure synthesis and design, that also can allow us to set design targets and feasibility, which can also be guided by the property model. because the property model will indicate certain ranges of feasibility for the different components, for the different set of conditions. And so that means the property model can also provide advice through the synthesis and design step. Now, one thing we wanted to look at is, are there other things we could do? Well, we could reverse the flow of information from the property model by actually solving the process model in terms of the properties and have the property model provide us the temperature, pressure, compositions, and component IDs. What that does is reduces the problem size significantly because you don't need to include the property model and all the component information in every simulation run. Now we're actually adding a solution role for the process model that the property model provides, and that's a key step in how we look at reverse design. So the concept of reverse design is really a two-step approach. The first one is to define the target. The second step is to match the target. And so one way to look at this is if you say a process model consists of two sets of equations, really. You have the balance and constraint equations that describe mass, energy, or momentum. And then you have the constitutive equations that is a representation of the phenomena, the thermodynamics, and so on. So those two sets of equations together make up the process model. If we were to separate those two and solve them separately, you actually gain a lot of benefits. So if we solve the balance and constraint equations in order to find the design targets or the constitutive variables, and then in the second step, we solve a reverse property prediction problem where we're only solving the constitutive equations to match these targets, that it really is a highly effective way of decoupling these complex equations, which typically, pardon me, the complexity is typically related to the constitutive equations. And so the key thing here is that as long as we match the targets, we will automatically have solved and satisfied the balancing constraint equations. So we don't need to solve those again. So we solve the balancing constraint equations to get the targets, and then we can solve the constitutive equations to match these targets. A key thing here is that this also allows us to have multiple property models to solve for the same variable, which typically you're not able to do in a combined process model. You would have one or a sequence of models that are applicable to different areas or a part of the design. Here we can solve them completely independently, and that makes it much more flexible. And so the way this can be described is that in reverse simulation, we're given the input stream variables, equipment parameters, and the known output stream variables, and now we solve for the constitutive variables. These are typically the property values or some kind of design targets. And then once we know the values of these variables, we calculate the unknown intensive variables, temperature, pressure, composition, and component ID, and even molecular structure can be solved at this part as well. And so one way to look at this more mathematically is to say, okay, we have a process with a series of inputs and outputs. In the forward approach, what's given is all the input variables. We have the feed stream specifications, the manipulated variables, we have the thermodynamic properties, and our design properties. And then we calculate our outputs. And if we're happy with the results, then we're done. If not, we have to go back and change the design parameters or the manipulated variables. And so this is a iterative approach. But if we were to solve this in reverse, we're solving this in a way where we're actually given the input variables, so the stream information and the manipulated variables, and we know what we want out of the process. And so what we're solving for is what are the design parameters and thermodynamic property values that will get us there. So that from a design perspective, from an engineering perspective, is a much more logical and effective way of doing things, because you're solving for a unique solution that gives you exactly what you're looking for, rather than having to go through an iteration to constantly try to improve until you get to the outcome that you were looking for. This is also effective if your desired outcome is actually not attainable, because you solve only one problem, and if you don't get viable solutions for the design parameters, then you know that you can actually achieve that goal. And it's much more effective to actually adjust your desired outcome, because you know that much better than you do the iterations you would do on the process parameters. So you can much better make those design decisions because you're making it on information that you have much more control over and what your desired outcomes are. So once you have these calculated thermodynamic values, you can determine the driving forces, which is a key part of the reverse design concept. So for any kind of flow operation, those are driven by pressure changes or pressure differences. Heat exchangers are driven by temperature differences, reactors by concentration differences, and separators based on composition differences. So those are the key concepts here. So when we look at specifically the reverse approach, the key thing is that at the maximum driving force, that's the core concept that we're going to talk about today, is when we have the maximum driving force, then we have the easiest conditions of operation, and that should lead to the minimization of energy usage, material, and work. And when we're looking at reactors, like I said, that's a change in composition. That's the driving force, the composition difference, and composition differences for separators. When we're looking at heat and mass flow, what we're looking at is minimizing the work needed to achieve the specifications for either temperature or pressure. So here's just a quick, simple example of a solvent-based separation, and we're going to solve this in reverse just to illustrate the concepts. We have a process, again, that converts raw materials to products. Along with the raw materials, there is a need for processed water. Goes through the process, comes in clean, comes out contaminated. And what we're going to do is an extraction process where we add a solvent to the system that removes the pollutant and returns some clean water. So the first thing we got to do is determine the target for the solvent. The solvent is unknown at this point, but we can calculate this from a simple mass balance. We know that the flow rate of the solute is going to be we're removing it 100%. That's our goal, and so it's the flow rate of the water going into the system minus the composition change in terms of the pollutant. The solubility is the amount of solute over the amount of solvent needed, and so we're trying to find the solvent to match this target for the solubility. We can do this in a number of ways. We can have data available, we can use models, but that's really the problem we're trying to solve. When we solve this in a reverse manner, rather than specifying a solvent, calculating all this and see if we're happy with the performance, and if we're not happy, then we have to pick a different solvent or a different flow rate and keep doing this until we get the solution that we're happy with. Solving this in a reverse manner is much more effective. So we can actually, for an example here, where we have a flow rate of 100 of the water, and we go from 1.8% pollutant down to 0. We can calculate how much pollutant needs to be removed, and we can specify that for a solvent, an orange solvent, let's say, the solubility has to be 1.8 divided by the flow rate of the solvent. And then what we're looking for is really, are there any solvents that give us a better performance than this? And for that solvent, now we're using a green font for this, we can calculate what the flow rate would be. Once you specify the solvent, that determines the extraction process and the relationship between the solvent and the solute that will determine the process parameters, temperature, pressure, so on. And once you have all the candidates, you order them with respect to the solvent cost and the operation. And the key thing is once you specify the solvent, that really specifies and fixes the solubility calculation. So this is a more effective way of solving this problem because you're going for the highest possible performance rather than constantly iterating and identifying the output to see if this is an effective solution to your problem. So when we look at using driving forces for design, what it really is a different way of representing the separation efficiency. And so in the first equation here, you have the standard relationship between the liquid and vapor phase compositions of a given compound using the relative volatility. In the second equation is driven, is set up by the driving force. Dij is the driving force for separation of compound I from J. And really it is, like we talked about a few minutes ago, it is the composition difference. And then there is a parameter here that is related, beta is related to the state variables of the system, so the temperature, pressure, compositions, and thermodynamics. The theory is that the driving force is inversely proportional to energy consumption and directly proportional to separability. So that means when the driving force is at its maximum, you have the easiest separation, and the easiest separation should relate to or translate to at least a close to minimum energy consumption, because less work is needed to accomplish the separation. And the driving force diagrams that are used for graphical representation of this is really a translation of a standard phase diagram. On the left, you have a XY diagram for different temperature and pressure. And on the right, you have the equivalent data represented in terms of driving force, where you have the separation efficiency on the y-axis and the same mole fraction of the compounds on the bottom. So how do we use this? Now we're going to talk about how we use driving force based design for VLE systems. So start with something basic, simple two-phase VLE model, and we can represent this with respect to either relative volatility, which is the classical representation, or with respect to driving force. So we have a feed stream with a certain composition, goes into our process at a certain temperature and pressure, out comes a vapor stream and a liquid stream. So we can write the equilibrium condition in terms of relative volatility, like I showed you before. We could also write it with respect to driving force. And then we can derive the mass balance either in terms of the overall streams, like here, or we can put in a representation where we use the L over V for R, and we can then substitute for the driving force. What does that do for us? Well, it allows us to plot the driving force as a function of composition, and you have a couple of extreme points to consider here. So when the driving force is 0, there's no separation. That makes sense. When either the liquid stream is 0 or the vapor stream is infinity, then you get a 0 for L over V, and that means the driving force is just the difference between the feed composition and the liquid phase composition. And if we go to the other extreme is when we don't have any liquid, then you get the driving force is related just to the feed composition, like this. The key thing in the steps that we use when we do this is for given feed information and composition, we specify either a liquid phase composition XI, a ratio of flows for the L over V, or the driving force, and we can solve it graphically. The key thing is that the driving force diagram here is calculated at fixed pressure, and each point represents composition and temperature. But we can do driving force diagrams for different pressures in order to get a richer representation of the system as well. So how do we use this in practice? In order to do that, we really want to go back and just quickly revisit the McCabe-Thiele method for how to do binary distillation. Not going to spend a lot of time on this, but just want to go through it fairly quickly. The equation sets for a standard binary distillation column here. We have an overall component mass balance here at the top. Then we have a description of the rectifying section in terms of the column profile, the same for the stripping section. And then the equilibrium relation is defined here at the bottom, same as it was before. Everyone remembers this from early chemical engineering courses. The McCabe-Thiele diagram really represents the the stripping section operating line here, the rectifying section operating line here, and the equilibrium curve. So when we're looking at using a driving force representation for this, so we have a mixture we want to separate into two products with a certain number of trays. And what we're looking for is what is the optimum feed location and what is the reflux ratio, which is the information that we typically get from the McCabe-Thiele diagram as well, but it's a more complicated way of doing it. If you plot it in terms of the driving force instead of just the composition, then what you're looking at is a curvature like this. That is the driving force for this composition range. And what we're looking for is the maximum driving force, which is located at this point right here. And there are rules in place for how to translate this information into design information. So for any system that we have, we pick two adjacent compounds. We can calculate the driving force diagrams, and we specify the two products. So in this case, points A and B are 100% pure of each of the two species, but it could be any points in the composition space. Then the operating lines is from the desired output to wherever the point is on the driving force, in the driving force space that we're looking at. At the top here, we have maximum driving force. Anything below that would be less than the maximum driving force, which then translates to, at the maximum driving force point, the slope of the curvature here will represent the minimum reflux ratio. Anything away from the maximum driving force will respond to a reflux ratio that's higher than the minimum. But what's nice about this is that it allows us to directly identify these operating conditions or boundary conditions if we're just trying to set the minimum reflux ratio, and anything away from that, we pay a penalty, but we're aware of that. But this is a very effective way of evaluating these types of options. And then there is a rule and a calculation here for how to get the feed location. It's literally related to the 1 minus the driving force times the number of stages. That gives us very, very close to the actual optimum value. And now we have all the information necessary to do rigorous simulation of this column to verify the performance. One thing that's nice is that there is a non-component specific relationship between relative volatility, maximum driving force, and number of stages. So for each value of alpha, the relative volatility of an adjacent pair, there is a corresponding value of the maximum driving force and of the maximum composition. And each of those are the maximum composition is the composition where the maximum driving force occurs. And that automatically corresponds to a number of stages, the feed plate location, and so on. And that means that this can all be pre-calculated for any combination of variables without even knowing the IDs. It's just a function of the relative volatility. And so that's a nice feature that these can be evaluated very quickly and then searched for if you have a system with a certain value of alpha. Without having to do all the detailed calculations, they can actually be pre-calculated and checked against rather than doing all the calculations from scratch. So how do we use this to design sequences of distillation columns? So the procedure is you order the driving force diagrams in terms of the maximum driving force, and then you configure the distillations in terms of this maximum driving force. And each distillation column is designed using the intersection of these lines. So here we have a driving force diagram for 5 species. So we will need 4 columns, and they're ranked in terms of separation efficiency. So this separation right here, which is the propane isobutane split, needs to be done first, because it's the one with the highest driving force. So that goes to the first column. The next most easy separation is this one. So that's the next split. Then you have 2 more splits to do, and obviously it doesn't matter what sequence those are done in. But again, they're arranged based on the highest driving force, and that makes it a much more efficient separation. and very easy to sequence without having to do any additional work. So, and then for each of these columns, we can design the feed plates and everything like that. When you start looking at more difficult separations, that's where you may have to look at hybrid separation schemes when you can't solve the problem with just a single column. So solvent-based extraction, distillation and pervaporation, pressure swing adsorption, all these types of combinations come into play when we're looking at maximizing energy efficiency, but we have complicated separation. So here's a plot on the right where we have a variety of separation techniques that have maximum driving force at different locations of the composition space. So at low concentration here, pervaporation has the highest driving force. Towards the end of the composition space here, distillation column or distillation separation is above a lot of the other technologies. And we even have extractive distillation in the middle here, where ideally we could make a system that maximizes driving force to a certain point and then uses the next one for the parts that are where that technology has the highest driving force. That way we're maximizing the utilization of the driving force and hence minimizing the energy requirements. So we don't want to complicate the system more than necessary. So we really need to think about when solvents are needed and when they're not needed in order to get both the separation that we're looking for, but also satisfying the sustainability targets. So here's an example where we're looking at evaluating a variety of solvents for doing azeotropic separation. And we'll talk about a specific example here in just a few. One of those that are classic is CO2 capture processes where solvents are used to capture CO2 from a flue gas and then regenerated and recycled. It's very, very energy intensive, and the choice of solvent is really, really important in terms of the efficiency of the process. You could also look at things like pressure swing distillation. If a azeotrope or the system is actually sensitive to pressure changes, you might be able to just change the pressure in a second column in order to get the separation you're looking for without having to add a third component. So here we'll look at different azeotropic mixtures. We'll highlight the acetone and chloroform. So here's the equilibrium diagram for a certain separation where clearly we have an azeotrope up here, which will limit separation given that the feed is here. And we still want to be able to get pure component out as one of the products. So we can evaluate the separation efficiency for these separations at different conditions, which will then allow us to do some simulation and so on and so forth. So the first thing we got to do is define the problem. Why do we need solvents? Which properties are needed? And so the wording of this problem could be, we have a binary mixture of acetone and chloroform, which is one we're going to look for in a waste stream. We need to remove the chloroform and recycle it back through the process. Benzene is known as a good solvent, but obviously being a aromatic and has a lot of environmental and health concerns, we don't want to use that. So what we're looking for is a good replacement solvent for benzene, and what does the process look like that can recover the chloroform. So, so we want to find a solvent that matches a certain distillation boundary. It's got to be selective to the chloroform, which is the B component here. It's environmentally acceptable, and we don't want to deform any azeotropes with either the acetone or the chloroform, because that makes it more complicated for recovery of the solvent later. And we want it to be miscible in the liquid phase. So that's got to be our starting point. And whether or not we can find a solvent that does this is the next step. But we always want to start with the kind of the perfect objective. This is ideally what we're looking for, and we can again adjust the constraints if we have to, but we will start looking for the quote unquote perfect solution first. So what we're looking for is some kind of solvent that has a distillation boundary that looks something like this. So it will cover the feed location of our system and go over to a point on the chloroform and solvent. Here there's a species defined in order to make it a 3-component mixture, but this is ideally the distillation boundary that we're looking for. And so our feed is here, and we want to mix the feed with the solvent. And so that will be, the locus would be on this line. Then we want to send that to a column that splits it so that out of the bottom comes a mixture that's only solvent and chloroform, and out the top is pure acetone. So that would be this operating line right here. And once we're at this point, which is right at the distillation boundary, then we can then take this mixture B1 and split it into pure chloroform and pure solvent, which is now being recycled and mixed with the feed. So that is how this would work. So from the phase diagram here, we can then back calculate all the properties that we need of the solvent and how it relates to the solutes. And that is what defines the computer-aided molecular design problem to actually identify the solvent. And so there's more details on this in webinar number 5 later this summer, but we will just briefly, kind of talk about that now, although all the algorithmic aspects and software aspects of that will be discussed in webinar 5. But what we find is we have values and information about what we want the solvent to look like. So in terms of boiling point, melting point, that's the ranges we can have here. We know something about the interactions between the solvent and the solute in terms of how strong we want the solvent to be, how selective we want it to be. We also can put some constraints on the environment, health, and safety properties. So lethal exposure limits, flash, partition coefficients, and so on and so forth. And these all require different property models. So the solvent properties, those are typically going to be pure component properties if it's a binary solvent, a single solvent. And you have mixture properties and phase equilibrium calculations to handle the solvent solute. We don't want any azeotropes like we talked about. These need to be calculated and verified. And then you have some properties that are temperature dependent, and so those are down here at the bottom. Some promising candidates that come out of solving the CMD problem for this. One of them is benzene. That's not surprising because that's really the solvent we're trying to replace, but that's not the one we're looking for. Others include 1-hexanal and methyl and pentyl ether, and a lot of other hydrocarbon solvents kind of in this size range. And so the next step is then we can set up an optimization problem to really evaluate all the different solvents, how they work in the process. And what we're looking at is minimizing the reboiler duty of the extraction column and the recovery column. And we have constraints on how much of the 5 candidate solvent in this case that we use, and we can use the number of solvents either being a pure solvent, or we can do a mixture of 2. The specifications are, for the first column, we want almost 100% recovery of acetone at the top, and all of the chloroform going out the bottom. And then the second column, where we're recovering the solvent, we want all the chloroform to go out the top, and the solvent or solvents to all be recovered at the bottom for recycle. And depending on how we formulate this and what it can be a mixed integer nonlinear problem, a mixed integer linear problem, or just a nonlinear problem, depending on how we specify the system, whether or not we allow for mixtures, and so on and so forth. And once we solve this problem, we can evaluate the performance of each of these and rank them. And so here we're just showing the best solution, where for the 1-hexanal solvent, we ended up with some objective function that was minimized at this value, and we get the information on the reboiler performance as well. We can also use the driving force method for design. And when we're looking at reactors, there's a concept of attainable region that we'll talk about here in a little bit, which indicates the highest selectivity of the reactor, and hence the highest performance. For separations, we want the highest driving force because that's corresponds to the lowest energy requirement. So when we look at these points, there is a relationship to how we can use this for control, because what we want is the lowest sensitivity of the output to the disturbances. So high disturbance rejection, you're going to get that, you know, at the this is the derivative of the composition change over the input here. So it's ethylene glycol and water. And similarly for separation, you want the highest sensitivity to the manipulated variable. That's how you're going to get the best possible controller response. And that occurs at the same set of conditions as where you get the maximum performance. So this is very helpful in doing controller design. You're doing this, going back to the question that was asked in the chat to Professor Ghani, this is actually being done at steady state without dynamics, because you're utilizing the inherent stability and performance properties of the system, which gives you a very good starting point for doing dynamic controller design once you've specified the rest of your process. So a few words about design algorithms. That's where we talk about the different types of unit operations. So here we're going to talk about reactors. We're going to talk about attainable region analysis. So here we have a series of competing reactions. So it's a system. We have A going to B, B gets converted to C. We can also have A being converted to D and B being converted to E. Our desired product is actually B. So that's what we're looking for. So what we're given is, in this case, the 4 rate constants, and we have the feed concentration of what's going into the system. And what we're hoping to design is a reactor network that maximizes the product B from pure A. So in order to look at these types of reactor networks, the degree of mixing is really important. So what we're going to do is actually do 2 extremes. One is perfect mixing, which would be a CSDR model, which you can see on the left, and a plug flow model, which has no mixing, which is the model right here on the right. And so we can take, for the PFR model, we can take the top 2 equations here, combine them into an expression like this, and then we can integrate it to get the concentration of B as a function of concentration of A. And that gives you the attainable region diagram that was developed by Professors Hildebrand and Glasser back in the early 90s. And so this gives you a representation of where, under what set of conditions can we maximize you know, the concentration of our desired product, which captures all the kinetics of these competing reactions that we're looking for. So there's a clear indication of where maximum performance is. And you can do this for different types of reactors as well. So you can see the dashed line here is for the same composition space or concentration space is what we get out of CSDR. And here the solid line is what we get from a PFR. And so the PFR gives us the maximum production of B at this set of conditions. And so now we're going to use the state space diagram for this reactor type that defines the attainable region. The objective, what we're looking for, is to maximize the concentration of B, like we talked about. It shows us that the maximum concentration is right here, about 3.8 moles per liter. And this can be done in a single plug flow reactor. Once we know the concentration, then we can calculate the residence time that is needed in order to get there. And once we have the kinetics, we can also estimate the temperature and pressure of that particular system and what the reactor should run like. And we can then finally either specify the flow rate, whether that is coming from our production requirements or feed availability, whatever the case may be. We can specify the flow rate or the reactor volume, which will give us then the remaining value. So flow rate specified, that gives us the volume, or if we specify the volume, that will put a bound on what our allowable flow rate is. So we looked at this already. So what we're given is the maximum attainable points of the driving force for the reaction. And what we're going to determine are the residence time, volume, temperature, conversion, and so on. And you can plot this as a function of temperature. So each curve is for a different reactor temperature. And you'll see in this particular example that there is a maximum where the attainable region, the maximum attainable point is the highest, and it's at one specific temperature. So if you only pick one of these, you can't guarantee that you'll be at the true maximum. So it has to be evaluated for a range of temperatures. But again, the method is very simple. It's very easy to calculate and provides an instant identification of what the maximum point is. When we look at heat transfer, we looked at separation, we looked at reactions. We have a simple system here. We can look at a stream splitter here where we're adding heat. Could be a flash drum or something like that. We have one stream going in, two streams going out, and we're adding some energy. We have two ways of calculating the outcomes of this. We can fix the outlet temperature, which is the same for both streams, and then we calculate the required duty to get there. Or we fix the energy addition, and we calculate the corresponding temperature. Simple rule for that, if you need to change temperature because two unit operations that are connected by a stream and they have different temperatures, you either need to add cooling or heating. The simple rule is to fix the temperature and back calculate the duty, because typically the temperature change or driving force is known, or it's a design decision. So you may have certain utilities only available that will dictate the driving force. And in fact, there was a question to Professor Ghani in at the end of the previous talk about the minimum approach temperature. That is something that is typically specified either for sections of plants or even plant-wide. So that might be known already, which allows you to fix the exit temperature and calculate the duty. Once you have the duty, you can identify the required utility amounts and the corresponding heat exchanger area. When you look at pressure changers, pumps, compressors, stream splitters, and so on, again, if you have two units that are linked, but there's a difference in pressure, then you either need to add a pump for liquids or a compressor. Same thing applies. You fix the exit pressure because typically the pressure driving force is known or can be set as a design decision. And then you back calculate the duty and the amount of required utility and other sizing parameters. So one thing to note here is that if you put pumps or compressors in recycle streams, where you typically will have some kind of purge, whatever the purge rate is will affect the flow rate of the recycle stream, and that affects the duty of the pump and compressor. Purge streams, they do have the potential of causing direct emission of greenhouse gases, so that is something to be aware of. There may have to be mitigation strategies put in place to handle that. And all these units, compressors, pumps, require electricity. And depending on the source of the electricity, that may also lead to greenhouse gas emissions for the process that need to be accounted for when you're doing your sustainability assessment. A quick side note here to think about, depending on the conditions, you may actually be better off achieving a certain pressure and temperature change by taking a gaseous stream, condensing it, and pumping it to a higher pressure and then re-vaporizing it. That depends on the specific conditions, but it's not always that you do everything on a gas stream with a compressor. It depends on the PV work, whether or not the compressor is the best way to change the pressure, or if you condense it first, pump it to the higher pressure, and then re-vaporize it. But that's a side note. Key thing here is to remember that whatever design decisions you make, even the ones outside the system boundary, are going to greatly impact the sustainability of the process. So if you're relying heavily on electricity for some of your units in your system, then it's really important whether or not that electricity comes from fossil resources or from renewable resources in how you define your sustainability metrics. So This is just a kind of an overview of the parts that we've covered today. So, you know, steps 4 through 8 of the 12 steps is really where we've been focusing on analyzing the base case design that comes out here, and we specify targets for improvement. And then the next set of steps is where you generate more sustainable alternatives. That's what's going to go into Professor Piscopoulos' lecture tomorrow. Once we have, you know, candidate solutions, we can look at thermodynamic insights, optimization, and so on to further refine those. And finally, we can pick the more sustainable solutions if there are any beyond what we had already identified. And so at the end here, I want to just go over a couple of small things to wrap things up. So how do we find these sustainable alternatives? Again, that's what Professor Piscopoulos will cover tomorrow. He's going to focus on process intensification, but also touch on circular economy, which will define some of the objectives for our designs, the different improvements that we can seek, higher productivity, better utilization of our raw materials, more resilient supply chain. We can look at using the equipment more effectively, increased efficiency when it comes to energy and water and so on. We want to make sure that we increase the safety and reliability of our process, and we want to improve the economic performance. How do we do this? Well, it may require changing the reaction pathways or optimizing the reaction conditions in order to minimize byproducts and so on. The species allocation specifically throughout the plant may be something that we need to look at. How do we utilize our raw materials and our utilities? Heat and power management goes into this when it comes to everything from heat integration opportunities and so on. You may have different types of units where you have benefits to the rate as a function of size. So certain systems lend themselves to downscaling and intensifying, and others you benefit from numbering up rather than just increasing size. And so those are things that need to be looked at. Same goes into the scale up and scale down. We need to think about those in terms of reliability and controls as well. And so once we've done all this, we should be able to get more sustainable designs. We'll get new networks from all these things. We'll have new integration schemes. We may have new intensified equipment, everything from reactive distillation columns to membrane distillation columns and so on. And those need to be factored into our option space, and eventually we'll end up with new processing routes that utilize all these. And so those are our more sustainable design. The key thing to remember here is that there's different ways that we can get more sustainable designs. Not all of these steps and all of these improvements are sought in every single scenario. So in the course that Professor Ghani has put together here, the key thing is really is to present a systematic method for how to analyze, set the targets, and generate alternatives and evaluate them. Because in some cases, you may be focused more on an environmental aspect rather than productivity or economics. All those things need to be looked at for each case. The key thing is that the method doesn't change. It's still the same method, but the target setting is the part that the designer has to focus on. So a few final comments and reminders for everybody. So these are the Sustainable Development Goals that the United Nations have covered, and several of these do impact directly the decisions that we make in the chemical process industry. And we have an opportunity to also impact in a positive way a lot of these particular metrics. I'm not going to go through them in detail, but they cover a lot of different things, but we'll talk about a few of them specifically. So when we look at the future, right now, if we don't change what we do, we're gonna, at some point, and some folks will argue that we're already surpassed the actual capacity of the planet already, which is why we're seeing climate change. I'm not going to get into the politics of that, but there's a pretty strong consensus that if we don't do something different, we are going to at some point certainly exceed whatever capacity our planet is able to handle in terms of the anthropogenic release of CO2 and other greenhouse gases. So there's no years here, but the key thing is we want to stay below the capacity limit. And if we make sustainability a priority, then we really can flatten this curve. But that's what's going to be needed, no matter whether, what these years are. If we don't change what is being done and how we do business, then we will certainly exceed the capacity. And so the goal for doing sustainable process design is to achieve at least one of these sustainable development goals. And the ones that apply typically to our field is like number 6, clean water. Number 7, affordable and clean energy. Let's see, what else we got? Climate, aquatic life, and terrestrial life. Those are the ones that we want to help improve. But we don't want to do it by having a negative effect on things like energy, on work and economics, on the cities and communities, and the responsible consumption. Those are the things that we have to look at. We can't improve the climate as the sole goal by not having a sustainable model from a business perspective. So these all need to be considered, which makes this a very complicated problem, but that is the business that as systems engineers that we like to solve. We like to solve complicated problems. So a couple things to think about real quick. And Professor Ghani mentioned this at the end of his talk as well. It's really important that you pick the right models, whether it's process models or thermal models. So here's just a very simple illustration of this. So this is a 2-column system for the styrene ethylbenzene separation. And over here, you have a plot that shows the consequence of error. So on the x-axis, you have the error in the alpha values, so the separation factor. And on the y-axis, you have an error in the minimum number of stages. So one is a consequence of the error in the separation factor. And we're only looking at plus minus 5% here. But you can see, if you have a positive error, so you're basically overestimating the alpha value, you're gonna get, lower cost because the minimum number of stages goes down, but you're actually getting below 0, meaning that you can't actually do the separation. So this is a very, very poor space to be in, because even though your economics might look good, your performance of the plant is not achieving what you actually set out to do. If you have a negative error, you will have feasible operation because you're going to be above the minimum number of stages, but it's going to be at a significantly higher cost. And if you look at some of these curves, if you had, at this one, alpha of 1.05, you're seeing a exponentially sharp growth here, and it's really a huge impact on the investment. But of the two, obviously the negative error one in this case is better, because you still are able to actually solve the problem that you're trying to address in your separation, but at a significantly increased cost. And so what does that really do? It means that, if your choice of model isn't right, you're not going to end up where you want to be. And so this is just, again, something to think about. So quickly to summarize here at the end, when we look at our field, chemical engineering in general, and process systems engineering in particular, we will have a key role to play, and we must play a key role in meeting our future societal needs. We've introduced through the last couple of webinars, and more will be coming through the series, some systematic methods for generating more sustainable design alternatives. The reverse design approach helps make these decisions regarding energy and operability easier. And for separation specifically, the driving force method is easy to apply. It promotes sustainability of the process because you're automatically minimizing the energy utilization and maximizing the driving force as your point of design. We do need to be very careful about consistency of the design specifications. We need a lot more work in our field to establish the use of the more non-standard unit operations, things like membranes, adsorbents, different types of intensified equipment, and so on, that are not readily available in commercial process simulators. We need to make sure that these are done in a consistent way so that we can get good results when we use them in the simulators for design purposes. If there's a tool available for doing the selection and design and evaluation of alternatives within a wide range of applications, that would be very useful. And you're going to see tools like that in the workshops later today. So finally, it is the call to action. We should all make sure that we contribute to the achievement of sustainable development. You all have a role to play. We all have a role to play. And that should be something that we're doing to help our industry, help our field moving forward. So with that, thank you very much. I think I ran a little bit long. I'm sorry about that, but I'm happy to take any questions you might have.
Thank you, Mario, for a very interesting lecture covering a wide range of topics. We can accommodate question answer. So let's see if there are any questions. Who will read out the questions from the chat box?
Yes. That driving force-based design is not very clear to me. Could you please explain that again for the stipulation part?
Sure. It's really not that complicated. So the driving force is a representation of the composition difference between the phases. And it's really just if you compare it to the McCabe-Thiele method, it's really just a coordinate change and a variable change, where instead of just looking at the curvature between composition Y and X, you're now looking at a plot of X versus the difference between Y and X. And that gives you an indication of where the, excuse me, where the highest driving force is at any point in the composition space. And that is what gives you an indication of the right operation. And there's all kinds of papers on that. I just placed one from Beck, Peterson, and Ghani on the slides, but there's going back 10 years, there's a whole bunch of papers that give a lot more of the algorithmic details on this, ranging from basic simple binary distillation going all the way to most recently, I think Professor Salas Cruz and Ghani have put a paper out on using it for reactive distillation as well.
Another question is, for reverse simulation, which type of model approach will be used, white box or black box, or others?
Well, it depends on if you're saying reverse simulation as in software, you don't really do software for reverse simulation. What you're doing is solving for a set of variables. And so you could argue that since you're solving for the constitutive variables, it's really neither. It's more black box than white box, because you're not solving the full design equations for the unit. What you're solving for is the design parameters, and then in the next step, you're solving the design equations that will get you that unit. So if you're solving for relative volatility in order to design a distillation column, all you're solving is the mesh equations to get the value of alpha. And then in the next step, you're solving the design equations that would for everything else in the column and the system that would give you that alpha value. So it's really neither black box or white box, because it's two different calculations. One is really separate from the model, the process model, and the other one, you're solving the constitutive equations very specifically. So one is more black box and one is more white box, I would say. But it's not the classical definition of those two, because you're solving it in two steps.
Is there any limitation of reverse design approach over tradition means, and it is practically possible to apply in industry?
the limitation in the reverse design approach is really limited to where we have model knowledge, which is not going to be any different than the forward design approach. If we don't have models available to describe the system, then that's going to be the limitation. But if a model or some representation of the system is available, then you can solve it backwards. That's really the only limitation. Whether it's practical to apply in industry, well, we got to remember where in the lifetime of a plant or the design process we are. This is at the intersection of process synthesis and what typically in industry is referred to as front-end engineering design. So we haven't gotten into the very, very detailed equipment design yet. We're only looking at that first front-end design. We haven't gotten into building anything yet. So yes, it's absolutely applicable in industry, but you got to be very careful of where in the design process you are. If your design is already set and you've started putting steel in the ground, then that's too late to start doing these types of analysis because your commitment's already there. But if you're trying either to do retrofitting of an existing plant or new greenfield design where you haven't committed to any particular layout or any particular pathway, absolutely this comes into play because you're looking at evaluating all the different options and you're trying to make your decisions based on performance rather than making equipment decisions and evaluating the performance afterwards. So it's a much more effective way of at least getting your long list of potential candidates down to a smaller list of promising candidates that will solve the problem that you're looking for. So that's where it comes in from a practical application.
Another question: does the reverse approach eliminate the iterative calculation fully or give solutions, for example, or design parameter in a fewer iterations than otherwise?
It depends on the specific problem. When you solve for the design parameters as the target, that's typically a unique calculation that is non-iterative. You may have to solve it multiple times for different set of conditions, but again, they're one calculation. They're not iterative in the classical sense. And then the second part where you match it, again, that is a single calculation to match the targets. The only way where you would calculate multiple matching of the targets if you use different property or process models for that part. But again, it's not iterative. You're solving, you solve for a certain set of parameters. That's one calculation, and the other part you're matching the targets. So you really relieve any need for iterations unless you're running case studies or you're trying to include things like a propagation of error or uncertainty analysis. That's the only time that you would have to have an iterative loop to check something. If everything is explicitly described, then it's a unique solution every time, or a unique set of solutions.
I think there was one more question that maybe you didn't see from participant number 50, Ricardo Duso.
Yes.
Can you read it out?
Okay. Is possible to adapt simultaneous design and control accordingly reverse design approach?
Yeah, absolutely. That I only did the one slide here. I don't remember the schedule, Rafiq. Isn't there at least some comments on design and control in one of the workshops?
Tomorrow we are going to briefly touch it.
Okay.
Maybe for the webinar series 2022, we can put the design and control.
Well, there's been a few papers coming out on this, mainly related to distillation column design, but a few papers have come out on this. Professor Manzouri at DTU and Salas Cruz and others. It's absolutely possible, because the premise is that you're designing your system to work at the best possible fundamental intrinsic point, not worrying about the dynamic responses, but just looking at where you're going to get the highest driving force, which means the highest sensitivity to change in the manipulated variable that gives you that will give you the best, conceptual controller response, and the highest level of disturbance rejection or the lowest sensitivity to disturbances. If you can design your control system to hit those two spots, then you're at a very, very good starting point for doing the full dynamic analysis and controller robustness, resiliency, and all those things. But you're starting out at a very, very good starting point because you've actually set the controller parameters at the right conditions. So there will be a few idiosyncrasies for different systems, whether you have inherent instabilities or cyclic processes that don't show up in steady state analysis. But again, if your controller design is based on having the strongest possible response to inputs and the highest disturbance rejection, that will give you a good starting point.
Okay, I think in order not to be too late for the other parts, we should thank Professor Mario Eden very much for this very interesting lecture and also for the very interesting question and answer. Thank you very much, and we continue.
Okay. Well, thank you, everybody. I hope you enjoy the rest of the webinars, the workshop, and thanks again, Rafiq, for the opportunity to present. So you all have a wonderful day now.